let's continue with our journey here. What we're going to start working on today is link design. And this is one of the central parts of this class. Because as an RF engineer, one of your major tasks is going to be link design. And today I'm going to talk about what is the objective, what is it that we're trying to achieve here, what are the individual elements that you need to take into account, and then a little bit of physics behind propagation that we have here, and a little bit review of some basic relationships that we have in all of communication, which is the Shannon capacity formula, and see how it applies to satellite communication and what we can learn from it just by looking at this particular scenario of its implementation. So let me first talk about what are the objectives of your link design. If you look at satellite communication, you have actually two links. You have what we call uplink or downlink. Uplink is the link between hub station or earth station to the satellite, and then the satellite receives the signal and then sends it back on the downlink. So you have, as I said, two links. What you as a link design engineer is expected to do is to dimension these two links, that the performance, that you meet performance specifications, and that the two transmitters and two endpoints remain connected over a certain period of time. Now, I speak about two links, but it actually, you have four links, right? If you look at two-way communication, then you have two uplinks and two downlinks. And here, even though the uplinks may happen and downlinks may happen on a same set of frequencies, you're really talking about two spatially separated points. So that comes into play quite a bit, because, for example, here, you may have raining in this area, but not raining here, and vice versa, or you can have asymmetry in those two links. The job of link design is to properly select all the components, to do the calculations, and to predict the performance of these links before you put the satellite in the orbit, because after you put it in the orbit, very little can be changed. So what are the things that you select, that you're kind of juggling here? You are taking into consideration transmit power, and again, you have, even though you have two links, they're largely asymmetrical. On an earth station, you're connected to a power grid, so you can pretty much send any power within the limits of what is allowed by the spectrum rules, right? You have to obey certain limits of your satellite spectrum. But on the other end, you have satellite, which is powered by the solar arrays, and then those solar arrays, they're not powering a single transponder. There's a bank of transponders, so there's a limit on the power on the downlink, and you have to take that into account. Then the second thing that we need to be dimensioned and selected properly, your antennas. And we saw that this is a balancing act between the gain, size, the pattern of these antennas, what is it that they need to cover. So you take all of these into account during the link budget analysis. Now, I guess transmit and receive antenna. Now, there are all sorts of things that exist on this path. I mean, we just draw it as a straight arrow, but you have a free space loss. This is the loss that is there because of the dispersion of the energy as the signal propagates. And there are all sorts of additional losses that you have to take into account. In one of the lectures, we're going to talk about them specifically, but it's easy for you to understand that if the signal is propagating with something that is not free space, depending on the signal frequency, you will exhibit additional impairments beyond the free space. In particular, let's say if you're at a relatively high frequency and you go through the rain will impact, and you will have the additional losses that you need to overcome. And what happens as a result of the additional loss, you may lose some of the signal strength, which may result in a reduction of your data rate, or in some extreme cases, the whole link might be broken. Now, the thing that is of importance here is that these additional losses are having temporal component to them. They're not constant, right? You cannot say it's always going to rain here in the dimension for the ring. But so there's the whole idea of the margins, calculation of the design margin that allows you to balance the reliability of your link with how much of the design margin you need to incorporate into your design. In addition to these environmental losses that I told you, and there are others like polarization losses and all that stuff. In addition to those, you have various sources of noise, right? And predominantly here, you have your thermal noise, the noise of a given temperature. And here we have asymmetry of the two links as well. However, we kind of a little bit luck out here. In what sense? Because the noise that we're talking about is the noise from the what is called black body radiation. If you point your antenna into something that is having a certain temperature, it will have some noise coming in, because everything that is not on a zero temperature radiates some energy. And if you look at these two, when the satellite antenna points to the ground, it cannot only see the hub station, it sees the stuff around the hub station. And whatever is around the hub station is not at the 0 kelvins. So there's some noise coming into the antenna here that needs to be overcome by the signal. So the signal needs to be much stronger than that noise, otherwise, or significantly stronger than that noise. Otherwise, the receiver at the satellite will not be able to demodulate. The other direction is true too. You know, the signal that is coming from the satellite needs to be received by the Earth station. But depending what is within the main beam of that Earth station, you may have a certain amount of noise. And luckily enough, this weak signal here is usually against the sky, which if your antenna is over a relatively narrow beam, then you see a small, tiny portion of the sky, and unless you have sun coming through your main beam of the antenna, you're actually working against much smaller noise temperature than the other way around. There obviously, this antenna is surrounded by warm Earth, so there's some of the noise that is entering through the side lobes, and also depending on what is the elevation angle, right? The higher you go up, you're away from the radiators that are nearby, so you end up having some reduction in the noise temperature. Whatever may be the case, you have to carefully consider the geometry and the antennas and what is it that you're pointing, and actually either calculate or measure the noise that you're going to be expecting in your design. Because ultimately, in every communication system, the noise represents the limit, how far you can go. Ultimately, you're going to reach that you're finding the thermal noise, if you're lucky, right? A lot of times you end up finding the interference and other signals that are present there. The thing that you need to know before you end up is what is the signal to noise ratio that you need to provide so that the equipment operates within the proper specifications. The signal to noise is for analog systems usually a measure. In digital systems we can quantify that as ZB over MT, but in whatever might be the case, we're working with some what we call receiver operating curves, which basically tells you to get sufficient performance, this is the signal level that you need to provide. Okay, so what we're going to be doing is addressing one by one all of these items. We talked a little bit about the antennas last time. So let's talk about free space path loss. So free space path loss propagation kind of starts like this. You have your signal delivered to the antenna. Antenna is, there are two components here on the right hand side. PT is what is referred to as conductive power. This is the power that you deliver to the antenna terminals, power in watts, that comes at the output of your power amplifier. This is fed into the antenna gain here, and the product of the conductive power and antenna gain gives you a radiating power, right? Now, radiating power is a function of the two angles. It is function of your both azimuth and elevation, because as we know, the antennas are spatially selective devices. They radiate differently in different directions of space. Now, a lot of times, implicitly when we say the EIRP of this transmission is such and such, what that means, this is the effective radiating power in the center of the main beam. So when I say ERP of 100 watts, that doesn't mean that the antenna is radiating 100 watts everywhere. It is radiating 100 watts in the top of the main beam, and you need to align the antenna properly to actually get that particular EIRP. Now, if you think about now this as a point source, and you think of it as radiating this power, then you can imagine a sphere that puts this point source in the center, and we can talk in terms of the flux density. Flux density is power per unit of area, right? If you think about a sphere, you can take this power and smear it on that sphere, right? And then you kind of get the total power distributed across the sphere. As the signal propagates, the sphere gets larger and larger, and the density of this power gets smaller and smaller, right? It's like blowing up the balloon. This density is going to be whatever is the ERP divided by the radius of the sphere. And this density is just like EIRP, which is a function of theta and phi. The density is also a function of the theta and phi. But if you assume that your antenna is aligned, then we can say in the main beam, the flux density or power flux density is whatever is EIRP divided by 4 pi r squared. And then as the signal propagates, this R becomes larger and larger, and ultimately one of these large spheres will reach the antenna. You can think of a receive antenna as a window in the wall that will let some of this the power density enter into the receiver. Now it should be obvious why the bigger antennas, physically bigger antennas, are better receptors, because they are actually sort of taking the power from the larger area of the space. So the way how we this is just a simplification of this equation, says that the power flux in the direction of the maximum radiation is whatever is the conductive power times the gain in that particular direction divided by 4 pi r squared. The receive antenna is characterized by its effective aperture. Effective aperture is given as a product of the actual physical size of the area of the antenna times some sort of efficiency that tells us the relationship between the physical size of the antenna and its electrical size. And the received power is going to be product of the power spectral density and effective aperture. It turns out, if you look at the electromagnetic theory, that the effective aperture of the antenna is directly related to its gain. Now, that's a very important symmetry. It teaches us that if the antenna transmits in a particular direction, it receives from the direction as well. So if I point antenna to transmit in this direction, it will actually receive from the direction the best. And the relationship between the gain and the effective aperture of the antenna is this one given here. So now we have that the power is the flux density times the effective aperture. If you take this expression and put it in the first one, you end up with this very elegant formula that says that the received power is proportional to the transmit power. The two gains, the gain of the transmit antenna and gain of the receive antenna, pointing at each other, right? Not the maximum gains, right? Because you can be mispointing, and in case you have some sort of loss. And then downstairs you get 4 pi r over lambda. R is the separation between the two, and lambda is the wavelength that you use for propagation. Out of these terms on the right-hand side, PT, GT, and GR, they don't change as a function of the separation. The only term that is a function of the separation is the term downstairs, and this term gives us a free space path loss. So free space path loss in a linear term is 4 pi r over lambda squared. That tells us how much of a free space path loss. However, very rarely it is used in this particular form. What we do is some basic math manipulation that are given in notes. We actually translate this linear equation into a logarithmic equation here. And we have these two formulas that are giving us free space path loss in dB. Now it's in logarithmic units. Now here you have two forms. One is if the distance is given in miles, and the other one is if the distance is given in kilometers. And then here you have frequency given in gigahertz, right? So it's slightly different than the one that we had in RF propagation, because in RF propagation we were having megahertz, but it's the same equation. It's just that because now this is 10 to the 9 instead of 10 to the 6, you have 60 dB here additional, right? It was 36.5 and 32.4, now it's 96.5 and 92.4. Some observation here is these are the signature of your free space. Your path loss increases 20 dBs per decade. So every time you go 10 times in distance, you're adding additional 20 dBs to a path loss. And then it also increases 20 logs of frequency. So every time you go higher in frequency, there are additional path loss that you need to overcome. Because of that reason, you know, it is typical. I'm not even aware if there is any case where it's otherwise. The uplink, the link from the ground to the satellite, is always on a higher frequency than the link from the satellite to the ground. Because you have this additional, you know, every fraction of a dB helps, right? So you actually move your path loss, move your transmission from the ground to the higher frequency, because you have more power available and more space to implement bigger antennas. What you see here on a chart is how much is the free space path loss as a function of the distance between satellite and the ground, and for the different frequency bands. It starts with this blue curve, which is at 1 gigahertz, and then goes all the way to the magenta curve, which is at 32 gigahertz, covering essentially your SC, X, KU, and KA bands. And you can see here that, you know, at the distance, which is your geostationary orbit distance, which is, I guess it's hard to see here, but this is 10, 100, 1,000, 10,000. So here at 30, 40,000, I don't know if this is in kilometers, so 40,000 kilometers, you end up with a very large losses there, all clustering around 200 dBs. 200 dBs is a huge number. That's 10 to the 20, right? So if I send, if I send 1 watt, I receive 10 to the minus 20 watts, right? So it's very, very minute energy that you receive after signal propagates over these large distances. So you need to recover. You have to do everything very carefully to be able to recover the signal after suffering such large loss. From this curve here, it would seem that it is more difficult to communicate at higher frequencies. That's not entirely true. If you think about all the things that are coming into play here, we learn that we see from this equation here that your path loss increases as 20 dBs per decade as a function of frequency. But what you're missing from this chart is this. Let me see here. This relationship here. If you move this lambda squared downstairs, or express your GR as 4 pi lambda squared. Let me actually do it over there. you can say that what I have here is that n times the physical size of the antenna is equal to the lambda squared 4 pi times the gain of the antenna, right? And this is true for both transmit and receive antenna. If you invert this, you end up that the gain of the antenna is 4 pi over lambda squared times efficiency times the physical size of the antenna. But this can be written as 4 pi c squared over frequency squared times. And if you just group things together, so what you learn from here is that the gain of the antenna for a given physical size, and let's say we maintain the efficiency the same, the gain of the antenna grows with the square of the frequency, or 20 dBs per decade, right? If you take 10 logs of this side, of both sides, you get 10 log of gain, which is the gain expressed in dBs, is 10 log of whatever I have here, 4 pi over c squared times a plus 20 log of frequency. So now you have three things coming into play. As you increase the frequency, your path loss increases, right? But you also, if you maintain the antennas of the same size, your gain of the antenna increases on both transmit and receive side, right? So now that means that if we go higher in frequency, we have some link budget advantages coming from our ability to focus our RF energy better to that satellite. Also, focusing the energy means that you can reuse your frequencies more tight, and there are definite advantages that are coming from going higher frequency. Now, what you don't see from either one of those is that there are additional losses that are beyond that of the free space, and these are the losses associated primarily with the rain and all the other impairments that you suffer along the ways that unfortunately increase with the frequency. So there are multiple things that are here in play. The thorough analysis of them will take us the good part of the semester, but you know, typically people will say, oh, when you move higher in frequency, it is always more difficult to communicate. It might not be the case. If you're in the area that doesn't have much rain, and then it might be advantageous to move to the higher frequency because you can use smaller antennas and achieve the same close the link just as good as at the lower frequency. Right? So be cognizant of these things. So it's not always a straightforward answer. It's one of those things that we're always kind of blamed. You know, when we always say, well, it depends, right? It always does. Okay, so let's see, we talked about this one, Several times I mentioned these additional losses. Where are these additional losses coming? There are several factors. I'm going to list some of the big ones, but as we progress, we're going to address them in more detail. But some of them are really easy to spot right away. There's misalignment of the antennas, right? You hope that you're going to be pointing the main beam towards the main beam. And a lot of times, if you look at that mechanically, you can actually do it. But what happens is, because of the changes in the atmosphere, the propagation of the signal is not always straightforward, especially if you're transmitting at lower elevations. So that means that you have to have the antennas in some sort of feedback loop that will help you maintain the point. Now, this is for static. If you have a mobile systems, then antenna pointing is a part of their operation. If you have a satellite on the move, let's say where your dish is on a vessel, or if it's on a vehicle, then you have to constantly make sure that the dish is pointing towards the satellite. There are atmospheric losses, you know, even though if you look at the entire length of the path, the path of the atmosphere is very, relatively short, but it's going through some things that have potential of introducing significant impairments. There is absorption coming from gases that are in the atmosphere, and when we get to that point, I'll talk about absorption peaks for oxygen and water vapor, which are major impairments for some frequencies. And there are also these hydrometeors like your rain, fog, and snow that resonate with electromagnetic wave that is of a proper frequency, and therefore introduce additional losses beyond the total free space. Radon is a cover of the antenna, right? If you look at a lot of satellite antenna for I guess corrosion purposes and just making sure that they have a lifespan that is sufficient, or if they're mounted, let's say, on the airplanes, then because of the aerodynamics considerations, you have to put some sort of cover on them. Well, the cover has to be usually of a special material, and that cover is called radon of the antenna. And there are some losses associated with that radon, because it's then there are component mismatch losses. You've all studied microwave circuits, so you've seen that everything needs to match along the way, and even if it matches at some point over time, you know, due to the component aging and other things, that there may be some mismatch between the components, which introduces additional loss in the transmitter or receiver chain. Now, these losses, sometimes you have a control of them, sometimes you can calculate what they are, sometimes you can spec them, and you can say, okay, it will work as long as they're not big enough. But oftentimes these losses may be so huge that you have to rely on the statistics, and you can say, well, I'm operating, for example, K-link, it's a very high frequency. Certain percent of the time it's going to rain so hard that my margin would have to be 40 dBs to overcome the pain. And then you say, well, I'm going to design this link, it's going to have so many seconds of outage per year. But I'll have to, in those cases when it rains, I'll have to reroute the traffic or do something that mitigates for that. Part of what we're going to be doing in link design is trying to quantify that. And you will see that there are some methods that allow us to do this trade-off and say, if you want the link to be of a certain reliability, this is how much margin you need to put on it, and this is what you expect to see over a period of a year or a couple of years or whatever is the average period. So typical designs are, I'd say 5 to 10 dB of margin. So that means that you are routinely transmitting slightly 5 to 10 dB more power than what is required to maintain the link, but then when something happens, you're still keeping the link on. And this depends on all of these components that we have here. So in general, we have our receive power function of what you transmit, your receive antenna, free space loss, and additional losses. What I'm trying to go through this is decompose all of these gains and losses into link budget items. And we'll ultimately, as a result of all of this, we're going to be developing several what we call link budget spreadsheets. The common engineering practice is to do this link design in something that resembles a spreadsheet where you account for all of the elements on the transmit side, all the elements on the receive side. There's a section for the margin calculation, and then you kind of work through your spreadsheet and make sure that everything is taken into account. That's it's not different than balancing, in many respects, than balancing your checkbook. That's why we call this link budget, right? Because you're budgeting for all of the gains and losses, and trying to take all of them into account. Before we go into there, I want to kind of review this section here, because this will help us understand some of the limits on communication in a satellite, and in general in a communication, but in particular here we're concerned about satellite systems. One of the fundamental formulas in telecommunication is this formula here, that's called channel capacity formula for additive white Gaussian noise channel. For the most part, you can assume that satellite channel fits this description pretty well. You know? It is for the largely non-selective, meaning it fits AWGN, but the signal is usually working against the noise that has additive white Gaussian noise properties. It turns out in this type of channel, this relationship holds. Now, what are the elements here? C is the capacity of the channel. This is the highest throughput or highest information throughput that you can send through this particular channel. B is the physical bandwidth of the channel, right? The ratio of C over B is called spectral efficiency. It tells you how many bits per second per hertz you can send through this particular channel. And then on the right-hand side here, you have signal to noise ratio, which is a fundamental measure of your signal quality. It tells you how strong is the signal against the background. This is the power of the signal, the power of the background. So what is so beautiful about this equation, it tells you the three fundamental things that we manipulate in communication, right? One is the data rate. You will try to maximize this, right? Always. Then the other one is your bandwidth, right? It tells you that your data rate is dependent on the bandwidth. If you make your bandwidth larger, hopes of getting a higher data rate, you know, are justified. And then here you have fundamental quantity that kind of juggles between the two, and this is the power of the signal. So you have power, data rate, and frequency. And this equation here tells you that you can always, if you pick the two, the third one is determined, right? You cannot set arbitrarily all three of them. You cannot say I'm gonna run 1 megabit per second over 1 kilohertz channel, and by the way, I'm going to use very low power. No, it doesn't work. If you want to do that, if you want to run 1 megabit per second over 1 kilohertz channel, then you'd better have enormous power to accomplish that, right? And that's what this equation teaches us. Now, here I don't think this is in the book, so let me spend a little bit more time here. If you define gamma, which is the actual data rate divided by the band of your system. So what are the units? The units are bits per second per hertz, saying this is how much of a data rate or information rate do I get per every hertz of the spectrum that I'm utilizing. Then you can say, okay, gamma has to be smaller than the maximum efficiency, which is obtained when you're at the capacity, right? So it has to be smaller than this. On the right-hand side, you have log 2, and then signal-to-noise ratio for digital systems can be expressed in slightly different terms. N0 times B is the power of the noise. N0 is the power spectral density, B is the bandwidth, right? So product of those two gives you power of the noise. EB is the energy per bit, but then times the bits per second of your data rate gives you the power, right? So if you say I'm signaling in 1 megabit per second, and then the energy per bit is this much, product of those two will give you power. So what I can represent this as EB times the rate, and I can represent this N as the power spectral density of the noise times its bandwidth, right? So now, if you look at what you have here, you have your R over B appearing on both sides, right? So you have that your gamma is smaller than log 2, 1 plus EB over N0 times gamma. And then if you invert here and you solve for EB over NT, you end up that EB over, or I say NT, N0, EB over N0, a lot of times you will have NT and 0. What's the difference? N0 is the power spectral density of the noise. NT stands for the total, right? So when I'm coming from cellular background, so NT always includes the interference, right? Here, most of the time it's just N0. Not always, but most of the time. So If you now solve for EV over N0, that gives you 2 to the gamma minus 1 over n. So that's just the math, right? So what's the significance of this thing? Well, gamma is a fundamental measure of spectrum utilization. What we strive in every communication system is to maximize gamma, right? Because your spectrum is a premium, right? And and you're usually having very little control about this B. B is what it is, right? You get this much of the bandwidth. What you're trying in your system design is to maximize R over B, right? To get the highest data rate possible for the allocated band. So that's the fundamental, and it tells you here if I specify what I would like to achieve in terms of spectral efficiency, this will give me the bit EB over N0. It will give me the bit energy over total noise power spectral density. This is my goal. This is a link budget item. This will tell me how much power do I need to deliver to the receiver, right? So let's look at what happens when you plot these two. You end up with a curve that looks like this. And this curve, you know, I don't know if I'm going to be able to explain it. It's worth you spending some time thinking about it. This is one that it will not come too much in problems, but it will come in your everyday understanding of what, when you look at the performance of any system, you know, not only satellite, but any wireless or even regular communication, wireline communication system. So this is how this curve behaves. So what is it that I have on the x-axis? I have the EB over N0 that I need to provide to the receiver. And what do I have on a y-axis? I have a spectral efficiency. So I would like to operate at high spectral efficiency and low EB over N0, which is really not possible. So what is possible? If you look at this curve, somehow, you know, conceptually, we divide this curve into two sections. We divide it into this section here, where the curve raise is quite steep, right? And we divide it into this section here, where the curve flattens out. This section here is what we call power limited communication. Why is it power limited? Because you see here that your ability to increase your spectral efficiency is primarily controlled by, it's always controlled by the power. But you can see here that even the small addition of the power, let's say I go I double the power, go from 2 to 4, well, I'm doubling the spectral efficiency too, right? So if I transmit at twice the power, I'm going to be able to get twice the rate, right? And this is where your I guess. So this is the area where we have what we call power limited system. Now, as you keep on increasing your power, then you end up in this part of the curve. In this part of the curve, you are what is called a bandwidth limited system. And in this case, you can see that in order to get 1 bit of the spectral efficiency, I have to go from 10, I have to go from 10 to 18 here in a power, right? So I have to increase my power significantly in the absolute terms. So this is when you become bandwidth limited. You are increasing your spectral efficiency 6 to 7. So what is that in percentage-wise? 7 over 6 is what, 1.1 and a change. So 12, 13, 14%, somewhere in there. So to get 10 to 15% increase in power, you have to increase in spectral efficiency, you have to double your power, right? Here, you get bit per second per increase, right? So 1 per 1%. I double the power, I double the spectral efficiency. So that's the sign of being band limited. Here, to get a fraction of the improvement in your spectral efficiency, you have to increase your power significantly. And the situation becomes even more difficult as you move over to the right? The progressively, it becomes harder and harder to increase the spectral efficiency. Contemporary systems that we have, in use today, depending whether they're new or old, but all the newer systems are in this portion of the curve. They're actually, we have, even for geostationary satellites, which are far away, we are most of the time able to get into the bandwidth limited area. Our power amplifiers are good, our antennas are good. So you're actually able to bridge this huge link budget, path loss, right? So what this teaches us is that going forward, we're actually have to be focusing on reusing our spectrum, because our ability to squeeze in more bits per second into what we already have allocated through just power increase is kind of diminishing quickly. And majority of the systems that are being designed today, and this is true for satellite and as much for all the other systems that we are designing, are actually facing this issue here, where pure power will not get you there, and we're finding ever more ways to reuse the spectrum, to find a way how you take the same piece of bandwidth and then use it many times, right, without excessive interference between the users. So this, I just wanted to put this here because it's extremely important. I hope you spend some time thinking about it and just go through this derivation and play with these formulas and get yourself calibrated intuitively. Say, if I have 1 megabits per second, what is it that I should expect in terms of throughput that I can get? What is theoretically possible? What is impossible, and so on, so that you get to understand where the numbers are coming from. Okay. So I have, for the remaining, let me go through several examples just of simple calculations that talk about stuff that I covered today. Let me first, I know it's trivial, but let's at least go through it once. This is the first example. It says, consider a geostationary satellite operating, so we have a geostationary satellite and operating frequency is 6 gigahertz, right? So it's a C-band satellite. So determine how large is the free space path loss in this case. So the satellite is at a distance, R is what we use, 42,134 kilometers. So that's the distance, and it says calculate the free space path loss. So the equation for free space path loss is going to be 9244 dB plus 20 log of your distance in kilometers. Let me just write it here. And then plus 20 log of your frequency expressed in gigahertz. So in our particular case, this becomes 9244 plus 20 log of 42,134 kilometers and plus 20 log of 6. And this gives you a number which is 200.15.
President, why do we take the center of the Earth? Like, why do we consider 6,378 kilometers?
Because I made a mistake, right? I apologize. Right? Exactly. So I just wanted to. It's good that I went through this example because I made a mistake here. I'm sorry. So let's just mention what Nav is mentioning here. What I mistakenly did in calculating the distance, I took the distance from here, which I shouldn't have done, because you cannot have a receiver in the center of the Earth. So you actually have to locate the point, on the globe. So this would be somewhat smaller, right? This number would have to be 134 minus 61 is 7.14. So I would appreciate if somebody has a calculator, so let's calculate.
That's 6378.
Yes, 6378.
Three five seven five six.
What is the result?
Hold on.
It is close to 200 anyway, that's why I didn't catch it.
199.
199,
99.
right? 199. So it's 200. All right, so that's the first example. Let me go through a couple more examples. This is the same as your example 4.2.1 in the book. It says you consider the satellite that's at a distance 40,000 kilometers. The transmit power, conductive transmit power is 10 watts. And your gain for the transmit antenna is 17 dB. Find the power flux density on the Earth's surface and power received by an antenna with effective aperture. So find W, an effective antenna, is equal to 10 to the minus 10 square meters. So find the received power for that one. So we have a satellite at a given distance transmitting this much into of the conductive power into antenna that has this gain towards the reception point. It says calculate the power flux density, and if the effective aperture of the antenna is 10 meters squared, calculate how large is the received power. W is the power spectral density, is the PD times the gain of the transmit antenna divided by 4 pi r squared. This is in linear, meaning that all of the units here are SI units, so we're not talking in terms of dBs, we're talking watts and pure gains and so on. So if we were to calculate this in linear domain, transmit power is 10 watts, the gain is 17 dB. How much is the 17 dB? 50. There you go. Times 50 divided by 4 pi times 40,000 times 10 to the 3 meters. And then whole thing is squared. So this ends up being 2.49 times 10 to the minus 14 watts per meter squared. So this is kind of the flux of the energy that impinges upon the surface of the Earth. And then your antenna is going to kind of suck from that energy flux. Now,
Question.
uh-huh.
Is the R altitude in this
No,
case?
it's just the distance between, the same remark is here, but this
Yeah.
is if you're equator, right? Let's say you're here, right? So it might be 40,000. I mean, let's not, obviously, that's the example given in the book, so I don't know if they cross-checked it, right? They just, the purpose here is to illustrate the calculation. The next one is the received power. Now the received power, we said, well, it's whatever is the power flux density times the effective aperture of the antenna. The best way how I envision it to this day is you have this wave coming in and it's coming through a window. And then this effective aperture here tells you how much of this energy you're actually capturing. The rest of it goes by you, right? Because you're just not big enough to capture it all. So in our case here, this becomes 2.49 times 10 to the minus 14 watts per meter squared, and then times your 10 meters squared. So this gives you a power of 2.49, obviously, times 10 to the minus 13 watts. Now, that's linear. Just like in every other area of RF engineering, in satellite communications we use logarithmic units. Unlike cellular communication, where the common unit was dBm, decibels relative to the milliwatt, here we most commonly work in dBW, decibels relative to the watt. So if I have a power that's expressed in watts, then the same power expressed in dBW is going to be 10 log of this power expressed in watts divided by what? Divided by 1 watt. Right? So if I want to express this particular power in dBW, my received power is going to be 10 log of 2.49 times 10 to the minus 13 watts divided by 1 watt, which gives you minus 126.03 dBW. For my RF propagation students and PCS students, we know that the offset between dBW and dBm is 30, but which way? That's always the question. Milliwatt is a smaller unit, so the number, when you express it in milliwatts, is always going to be a larger number, right? Because you're comparing it against a smaller unit. So if this is my 26, so this is the lower of the two numbers. So if you want to express it in milliwatts, it needs to be 30 dBs out, right? So that's the formal relationship in dBm is going to be whatever is the power expressed in dBW plus 30, right? Because this is dBm is smaller units, so 1,000 times smaller. So there's a 30 dB that you need to have. So if you want to express this power in dBm, it's going to be minus 126.03 plus 30, everything in dBm. And this is minus 96.03.
Do you use dBW just because their transmitters are transmitting lots of power rather than milliwatts of power?
It's a cultural thing. There are, I guess when I really don't know. I mean, it's either way. I mean, it's not like it's just a cultural thing. I mean, you can work with dBm just as good as you can work with dBW. I think how these things get, I can speculate how these things get started. There's a field in development, and then somebody sits and writes a really good book, whatever they adopt there. That's what we end up using, right? So I guess if I were to trace back dBm, on my bookshelf it goes to like early 70s, like Jakes and all of these guys wrote microwave communication, where it's actually, that's how it's been copied. This book has been copied in all the books since, right? And that's why we. But you usually, I don't know. I mean, you usually pick whatever is convenient. Right? You will see. I'll when we do link budgets, I'll point to you where the subtle differences are between how I taught you things are done in cellular and how the things are done in satellite. Like, it's very common that they say power spectral density. You remember that number 4 times 10 to the minus 18 milliwatts per hertz? Well, they don't say it that way here. They say minus 174 dBW per hertz. Right? So where is that number coming from? Right? I have to kind of explain it to you. We're still gonna use all of them because you're in school, and I want you to understand physics. And then when they start throwing dBs at you, it will take you a little bit of time to learn how to calculate. I'll do some of these calculations as I see satellite guys do them. You will see how they tend to add hertz and dBs and all that stuff, which I try to avoid just for the clarity, academic clarity. But once you start practicing in the field, then you become just like your environment, just so that you can communicate more effectively. Okay, so let's do one more example. So this is example 4.32. It says the satellite in this particular, in the first example, operates, so the frequency now is 11 gigahertz. So this is a what band? K band. Right? This is a K band satellite downlink. The RX antenna is given as, so the GRX is given as 52.3 dB. And find the received power, right? So here's the situation we have. We have a satellite with its antenna. It goes all the way to the Earth, where there's a dish here. So at this end, we have the transmit power as conductive transmit power is 10 watts. It goes into antenna that has a gain of 17 dB, right? And then it's received by it travels on 11 gigahertz, and then your receive antenna here is 52.3 dB. Now, why is there such a difference between these two antennas? Because one is on the satellite, it has to be small, portable, and all that stuff, so that it doesn't introduce much weight. This is a huge dish sitting, on a, what's that road by the airport where Harris said those huge dishes? That is very large, and therefore it has its ability to focus energy is tremendous, and this is a huge gain. So remember how we do these calculations. We first calculate EIRP. So what's EIRP in this case? It is your conductive power expressing dBW plus the gain expressing dB. What's the conductive power in dBW? If it's 10 watts, how many dBW is that? 10, right? So this is 10 dBW plus the gain is 17 dB. So this is 27 dBW. That's your EIRP. The next thing here we have is free space path loss, which in our case becomes 32. We calculated it, so it's still on the board, right? We did it, huh?
Yeah.
We did it, Chris. Did we? No. So it's
Yes, 1 minus.
huh? It's not there, right? This is different. So let's just do it. It is 92.44 plus 20 log of 40,000 and plus 20 log of 11 gigahertz. And this, I wonder if I did it here. This ends up being 205.3 dB. And then your received power in dBW is going to be your EIRP. dBW minus your free space path loss expressed in dB, and then plus your gain of the receive antenna expressed in dB. So this is your 27 dBW minus 205.3 dBs, and then plus the receive antenna gain, which is 52.3. And when you do all the calculations, this is minus 126. So this kind of helps you calibrate your feeling about what are the values that you should expect, right? Around minus 120 dBW, minus 100 dBm, those are the received powers. Now, whenever we do these kind of examples, there's an obvious question that I always get. And, if you look at this equation here, you're adding some units that are not, the unit is not the same, right? There's dB and dBW and subtracting and adding. That always comes up because people are just not fluent with calculation with logarithmic gains. Now, There's an appendix in the book that talks specifically about it. And there's also one RF propagation class that we have on a website where I talk particularly about working with logarithmic units. If you feel a little bit shaky, then make sure that that you review that. It's extremely important because if you start adding dBWs, it's questionable whether it's not just it's not just, oh, I messed up, right? You don't really know what you're doing, right? You can subtract dBWs and the result is in what? In dB, and this is your signal to noise ratio calculation. But adding dBWs means you're squaring some power. And if you're squaring the power, you better have a good justification for doing it. I don't know what would be that justification, but you might have, right? As long as you know what you're doing, you should be able to defend it. But make sure you review those, because I do that in RF propagation. I review it a little bit in a PCS, but here I don't have much time in this course to go through that. But I'm expecting that you know it, right? So that you're fluent with these, and there's no question what operations are valid and what the result is valid. So, any questions here? So these two problems kind of give you basic idea about what the link budget is about. Here I'm doing the elementary link budget, right? I'm saying if I transfer this is what it goes through these kind of antennas. This is what I should expect. Obviously, I'm simplifying this and neglecting a lot of terms that we have to gradually put back in until we actually get to the complete spreadsheet of calculating. Okay, go ahead.
You're neglecting the losses in antennas?
I'm neglecting everything now. I'm just doing 4 terms, right? Because I want you to get the big idea. This is the first order approximation, right? And people that do this for a living do this in their head, right? And then they say, okay, secondary things. Let's calculate, the losses in waveguides. Let's calculate what is the margin due to the rain. Let's calculate. So we'll get there, but I want you to get the basic concept how this works. It's almost like just like big. This is your paycheck, and this is the big expenses, and then later on you start adding your coffees and sandwiches and all that. All right. So that's it for today. We finished a little bit early.